Okay, yeah, good morning and welcome to the second actually of the two webinars associated with the SPARC 1051 project. This is a project funded by UKIERI and the Indian government. And it has actually the idea of promoting research, education and outreach in India and between India and in this case also the UK, exchange of research, education and knowledge between actually the two countries in this particular case. And I'm indeed very happy actually to have here today one of the participants of our SPARC project, Professor Tiwari, and also Dr. Shimjith. They will be holding actually a very special talk today on control. And BARC obviously is as a specialist institute part of our SPARC project and has been actually a very important use case provider also. Okay, I would like to hand over to Professor Tiwari and thank you very much again.
Thank you. So I too welcome all the persons who have joined this webinar, and the webinar consists of two parts. One part, short one of about 5 minutes, will be presented by me, that is on the activities of Homi Bhabha National Institute and in particular of our research group at Bhabha Atomic Research Center. And the other part will be completed by my colleague, Mr. K. Sairam. So, with your permission, I would like to share my screen from this end. So, I hope it is visible, my presentation is visible to everybody on their respective ends. Is it visible that end? Could somebody please confirm?
It is visible if you just like to make it full screen.
Thank you, thank you. So, as I told, a very short presentation of about 5 minutes about Homi Bhabha National Institute. So, this institute was established on June 3, 2005 as a higher education institute in our country. And it is a cluster of 11 eminent institutions under the Department of Atomic Energy, Government of India, with an emphasis on multidisciplinary research for addressing national needs. So there have been universities in the other parts of the world on the similar line, cluster universities. So for example, in United States, Jet Propulsion Laboratory funded by NASA is operated by Caltech, California Institute of Technology. Sokendai, a graduate university for advanced studies in Japan, was established in 1988, which runs only doctoral programs. And Paris Saclay University, which is established recently in 2019, shares resources of about 275 laboratories, and it is again a cluster university. So the idea is that we have research laboratories, there we have costly equipment and facilities, and if they come under ambit of one university, then the facilities will be available to students. So it is a university in lab environment rather than lab in university, which is a conventional way the universities are generally established. So Homi Bhabha National Institute has its constituent institutions, which are research and development centers. Among them are Bhabha Atomic Research Center, Indira Gandhi Center for Atomic Research, Raja Ramanna Center for Advanced Technology, and Variable Energy Cyclotron Center. There are grant in aid institutions, which are Saha Institute of Nuclear Physics, Institute for Plasma Research, Institute of Physics, Harishchandra Research Institute, Tata Memorial Center, and Institute of Mathematical Sciences. We have one center called as Off-Campus Center, which is National Center for Science Education and Research. Now the students who are undergoing the various programs of study at these institutions under the ambit of Homi Bhabha National Institute, they join these institutions as well as they go to these industrial units which are Nuclear Power Corporation of India Limited, Nuclear Fuel Complex, and Heavy Water Board. We have some more which I have not listed here. So this university was accredited by our National Assessment and Accreditation Council with a score of 3.4 out of 4, which puts it under the category A university, and it was done recently in 2021. Then we have Ministry of Human Resource Development. In that National Institute ranking framework, again in 2021, this university was ranked 18th in the university category and 36th among all the 1650 institutions in the country. This institute runs 44 academic programs leading to degrees and diplomas in a variety of science and engineering disciplines, including mathematics. Since 2005, 2006 PhD students have graduated and 1424 MTech students have graduated. So I think I did not mention this institution is running only postgraduate education, that means MTech, MSc and PhD programs. These are a few of the academic programs of Homi Bhabha National Institute. PhD, integrated PhD, which are of two types, single degree and double degree. PG diploma in engineering sciences, chemical sciences, life sciences, physical sciences, and fusion imaging technique. MSc in engineering, clinical research, physics. Again, MSc in NMMIT, which is, I'm forgetting, I think nuclear medicine and medical imaging techniques. And MSc hospital radio pharmacy. We have integrated MSc programs in various disciplines like chemical, life sciences, mathematical and physical sciences. We have PG medical degree, MD, super specialty medical degrees, DM and Master of Chirugwe, and diploma in radiological physics. So our research areas span a lot of multidisciplines like material development and characterization, multi-scale modeling, microstructure property correlation, process metallurgy and thermodynamics, evaluation of refractory and rare earths. These are generally in the metallurgical sciences. Then in thermal hydraulics, like thermal hydraulics of advanced reactors, severe accidents research, computational fluid dynamics, modeling for simulation and solvent extraction contactor. Chemical engineering like fluidized bed denitration for nuclear streams, then recovery of nuclear materials from secondary streams, microreactors and isotope separation. In civil engineering, life assessment of structures, components and systems, and then solar thermal energy research in environmental sciences. Again, in control and estimation, high voltage RF cavity and waveguides, pulse power supplies, electron beam vapor deposition, signal processing, nuclear detectors, medical electronics and imaging, high-speed data acquisition and ASICs, formal methods and verification, system computer information security, robotic vision and navigation, ultrasonic systems, then trace gas dissection techniques, cable health and diagnostic. So these are the various areas. However, particularly in our lab, we have been mostly pursuing research in mathematical modeling, control, estimation, and fault detection. So in this, I just want to mention that out of our effort, we have been able to make a real-time simulator of a nuclear reactor where we can study normal and off-normal conditions of a plant, of course not the accidental situations. And this is mostly used to validate the C&I systems design using a hardware in loop kind of testing. we have done some control studies based on the linear quadratic regulators, sliding mode control, etc. Conventional output feedback also we have done, fast output sampling, periodic output feedback. I want to mention that in 2006, our Tarapur atomic power plant was facing a lot of instability issues. So we did analysis based on the most simple linear stability analysis. We redesigned the controllers and we applied our knowledge to solving the real life problem in the 540 megawatt Tarapur atomic power station. In the area of estimation, we have again developed a reactivity meter which is used in our small nuclear reactors for measurement of reactivity worth of burnable pins, fuel rods, and protection devices. In the fault detection, we have, sorry, I went backward. In the fault detection, we have applied this principal component analysis and other techniques for sensor fault detection and diagnosis in the some areas of nuclear reactors. Now with this, I would like to hand over to Mr. Sainam, and he will go ahead with the part 2 of the presentation.
Hello everyone. As Dr. Tiwari has explained, our major area of work was related to modeling, control, estimation and fault detection with applications to nuclear power plants. And central to that is a mathematical model of nuclear reactor core, which will be the topic which I will be presenting today. And pertaining, basically I will be talking about mathematical modeling pertaining to control studies. In this talk, I will be covering the overview of how mathematical equations are derived, emphasizing the need to understand thermal hydraulic coupling and model the nuclear reactor dynamics in along with the thermal hydraulic models, and then followed by some of the open loop transient simulations for a typical PWR core. So in context of nuclear power plants, mathematical modeling is used in design and safety analysis of the core under normal operating conditions as well as under abnormal conditions, and also in development of real-time training simulators for control room operator training and licensing, and also in real-time engineering simulators, which are being used these days widely in the design phase of the nuclear reactor for verification and validation of the control algorithms, and also for verifying the prototype hardware systems using hardware in loop testing. In addition to this, mathematical models are used in control studies, specifically for designing the controllers under nominal conditions and also to carry out linear stability analysis. When it comes to approaches of modeling, as it is not suitable to obtain various transient data from an operating power plant, we always resort to first principles modeling approaches in modeling the nuclear reactor dynamics. However, whatever correlations and data we obtain from test loops, we use them in simplifying the governing equations. And in specific, I will be focusing on thermal reactor, where the nuclear fission chain reaction is sustained majorly by the thermal neutrons. So the slide shows the life cycle of a neutron from its birth, from a fission reaction until its subsequent absorption either in a fission reaction or a non-fission absorption. So a thermal reactor consists of fuel and coolant and moderator. Coolant for transporting the heat generated in nuclear reactor, moderator to slow down or thermalize the neutrons, fast neutrons that emanate from the fission reaction, and the reflector surrounding the core to prevent the leakage of neutrons from the core region. So as shown in this schematic, whatever neutrons that are emitted following fission, most of the neutrons will be prompt neutrons. However, some of the neutrons will also be liberated from the beta decay of fission products, and this fraction, even though minor, significantly helps in controlling the nuclear reactor dynamics. So these fast neutrons undergo scattering collisions with the lighter nuclei, and then in that process they get slowed down. Some of them gets leaked out from the core region, and they cross the kind of wall called as resonance wall, wherein non-fission absorption takes place within the fuel itself, and then whatever leftover neutrons that are there, they thermally diffuse, and finally they get absorbed in a fission reaction, or they get absorbed in a non-fission reaction. So with this, we can understand that the neutron dynamics within a core thermal reactor is a function of energy, space, time, and also it is direction dependent, considering the transport phenomena of the neutron. Since reactor power is proportional to fission rate, which in principle is proportional to neutron flux or the neutron concentrations. So to understand the dynamics of a reactor power, we have to understand the dynamics of neutron concentration or neutron flux. So even though the fundamental governing equation is transport theory, diffusion theory based approximation is widely applicable and used in the nuclear reactor analysis. In the diffusion theory, first the continuous energy spectrum of neutrons are converted into a discrete energy groups, and then depending on the number of energy group, we have one group diffusion theory or multi-group diffusion theory. Specifically in multi-group diffusion theory, two energy group theory, or where we discretize the energy group into a fast and thermal neutron group, and one group diffusion theory are used in modeling of for control studies as well as for real-time simulators. Many energy groups are generally of significant interest to physicists, which they use in the lattice calculations or design calculations. So coming to the one group diffusion equation, it is nothing but a neutron balance in any arbitrary volume V. So time, as shown in this equation, time rate of change of neutrons in any arbitrary volume V is equivalent to production term minus absorption in the volume V and net leakage from the V. So net leakage term, since we are approximating with the diffusion theory, can be directly written in terms of the flux gradient using Fick's law. And the source basically consists of two terms. One is the neutron generations, that is prompt neutron generation term, and the other one whose dynamics is dependent on the decay, beta decay of the precursors. Generally, these precursors are grouped into 6 normally or more conventionally. And then in addition to this diffusion equation, we have to study the time dependent dynamics of these precursors to account for the total neutron source production within a volume V. Usual approach to solve this PDE is separation of variables and to space dependent term and time dependent term, and by assuming that the time independent space function, or assuming that the fundamental shape of flux within a core doesn't vary much with the time, we can obtain a set of ordinary differential equations, which is popularly known as point kinetics model of a nuclear reactor, where it consists of dynamics of neutron concentration and the precursors, and a term known as reactivity rho is an input to this, can be considered as an input to this model, which indicates the core reactivity status. In case of a subcritical reactor, rho will be less than 0, and a supercritical reactor, rho will be greater than 0. And for a reactor generating constant power, rho will be 0. Basically, control of reactor is by adjusting this reactivity. So typical response of a point kinetics model to step change in this reactivity is shown. As we can see, when there is a step change in the reactivity, there is an initial prompt behavior followed by an asymptotic behavior of the neutron density. This characteristically different behaviors make this equation stiff, and also emphasizes the fact that even though the delayed neutron fraction is less, the asymptotic behavior of the neutron flux is mostly governed by those delayed neutrons for reactivity values less than the beta, the fraction of the delayed neutrons. That's why from the safety point of view, the allowable reactivity perturbations in a reactor are kept many orders less than the beta. So this set of equations are widely used in studying the nuclear reactor dynamics. However, this model is only applicable to the tightly coupled reactors. As in tightly coupled reactors, I mean, in the previous slides, I have shown the neutron life cycle, where it is starting as a fast neutron and it is traveling until it gets thermalized and again finally gets absorbed. So the distance a neutron travels from the time it is born as a fast neutron until the time it is absorbed is basically represented in terms of a migration length. So if the physical dimensions of reactor are comparable to the migration length, then we call such reactors as tightly coupled, and there won't be any flux tilts or spatial related issues in such reactors. So point kinetics model is a very good approximation of such reactors. Whereas if the reactor physical dimensions are many orders high in comparison to the migration length, such reactors are prone to spatial oscillations, which are mainly due to the xenon fission product, and such reactors are generally termed as loosely coupled reactors. And for that reactors, point kinetics model alone cannot be used to understand the temporal and spatial behavior of neutron flux. So just a quick glimpse of how the xenon is actually affecting the reactor dynamics. Xenon is one of the fission product, even though its production its contribution or yield is very less. It is having a very high thermal neutron absorption cross section. Due to this, the dynamics of xenon following any instantaneous flux changes will be opposite of the direction in which the flux has changed. For suppose this graph shows when there is an instantaneous flux reduction, xenon concentration initially builds up because of reduced absorption, and after a long time it achieves peak and its behavior starts inverting. Such kind of inverse behavior poses a serious control problem where there can be out of phase spatial oscillations in loosely coupled reactors. So how these oscillations can occur and in which direction they occur, just we will consider. So any 3D problem, we can consider oscillations of three mode. One is azimuthal type of oscillations, or radial oscillations, or axial oscillations, wherein this plus indicates one half of the core and minus indicates other half of the core. So this power in one half of the core can have a opposite trend, while flux in other half of the core will have an inverting trend in case of any spatial oscillations. So higher order harmonics are also possible depending on the type of reactor or the dimensions of the reactor. So here I have shown a simulation where a typical PWR exhibits xenon-induced spatial oscillations. PWRs, the control rods are normally distributed radially so as to avoid any asymmetric reactivity perturbations along radial directions. However, for power maneuvering during power operations, these control rods move from top of the core to bottom of the core, towards the bottom of the core. So this can lead to asymmetric perturbations along the axial directions, and if left uncontrolled or unmonitored, they can lead to out of phase oscillations as shown here. Even though the total power remains more or less same, we can see that one half of the core starts generating more power and other half of the core starts generating very less power. So on one side, the core thermal margin limits may be exceeded, and it can be a serious safety concern. For this purpose, in PWRs, generally axial offset is monitored during normal operation, and if required, the spatial control is invoked automatically to ensure that axial offset is within the target band. Similarly, we can there is one reactor called as advanced heavy water reactor, which is a boiling water reactor with vertical pressure tube type reactor and using light water coolant and heavy water moderator. This reactor has very large radial dimensions, due to which azimuthal neutronic decoupling can happen, and xenon-induced spatial oscillations can occur along azimuthal direction if not monitored and controlled. So hence, to study the dynamics of these reactors, we need a space-time kinetics model, but not a point kinetics model, and both for simulation as well as controller design. So there are many standard techniques that exist in the nuclear reactor domain to model such reactors, which include model methods, flux synthesis methods, or nodal methods. So multi-point kinetics modeling, which is a model developed under nodal methods framework, is prominently used in control and simulation studies, which I will be presenting. So again, the initial or the governing equation will be the diffusion equation, albeit in case of two-group diffusion equation, we have to write the diffusion equation for fast flux and thermal flux separately. The source term remains the same, and it occurs only in the fast flux dynamics, because whatever neutrons that are released subsequent to fission are fast neutrons. In addition to that, we have scattering terms, where there can be an upscattering of thermal neutron gaining some energy and converting into a fast neutron, or fast neutron losing some energy due to scattering and coming to a thermal neutron. So these two scattering terms will be additional terms that gets included in case of a two-group diffusion equation in comparison with single-group diffusion equation. All this absorption cross-section, diffusion equations, and the fission cross-sections, this set we call them as a two-group parameters, and these parameters normally are dependent on the moderator properties and the coolant properties in the reactor core. So since those diffusion equations are partial differential equations, one method to solve them is to discretize these partial differential equations along in the spatial directions, in all the spatial directions, by dividing the core into number of non-overlapping core meshes called as nodes. And each node can be characterized by a set of homogenized two-group parameters, and each node can be defined with a homogenized flux, which is a volume integration of the flux within that particular node. In this manner, by integrating the differential equations in a node, we can get rid of the partial differential terms that are there with reference to flux, and then with reference to the leakage term or the diffusion term, we can have a coarse mesh finite difference approximation. By enforcing continuity across the boundary, we can approximate the leakage term as a function of adjacent nodal fluxes and a coupling coefficient, which signifies the coupling between adjacent nodes. This coupling coefficient determines the coupling between two nodes and is a strong function of the node geometry and also the diffusion coefficient. In this way, we can integrate the diffusion equation, which is a partial differential equation, and we can obtain a set of ordinary differential equations within the node, which can be readily solved in time to obtain the dynamics of fluxes within each node, thereby obtaining the temporal as well as spatial behavior of reactor. However, further approximations can also be done to obtain the differential equations directly in terms of power, which can be used mainly for control studies. Till here, this set of equations are mainly used in simulators, whereas further approximations are also possible for control studies to reduce the model order. So by defining a spectral index, that is ratio of fast flux to thermal flux, and assuming that it can be completely defined in terms of two-group parameters, we can convert that two-group diffusion set of two-group ordinary differential equations into a single power dependent equation by using this approximation, which is normally known as a 1.5 group approximation. So final set of equations within the node can be shown here, can be seen here. So which is known as actually a multi-point kinetics model of nuclear reactor. If we closely observe, this is addition of two terms. One term signifies the point kinetics model behavior within the node, and other term signifies the coupling between adjacent nodes. So now when we talk about nodalization schemes, in case of PWRs, which are more prone to axial spatial oscillations, we try to nodalize the system along axial direction and try to find the properties of this neutronics model, whether it is capturing all the unstable eigenvalues or not. And then we can decide the nodalization scheme accordingly in case of PWRs. Similarly, in case of BWRs, the HWR reactor which I have talked about, there are more spatial oscillations along azimuthal directions. So core is normally divided along radial direction to obtain the nodal model. So this is how we generally start from a transport theory with approximating using diffusion theory and end up with a finite set of ordinary differential equations which are coupled together. The reactivity term, the net reactivity term in node H, but this term depends on the, as indicated earlier, the two group parameters manifest in terms of reactivity after change of variables. So this reactivity depends on the properties of the coolant moderator, as well as amount of xenon present in that particular node, and also the external reactivity which we add in terms of control rod moment. So net reactivity can be considered as a addition of various terms as shown in this block diagram. So this reactivity, if we consider it as a input to this core neutronics model, so power can be considered as an output, and this power can affect the thermal hydraulic properties of coolant moderator and also the xenon, and in return the concentrations of xenon or the properties of coolant or fuel can affect the reactivity, net reactivity within the node. Since the characteristic time constant associated with each feedbacks will be different. For example, thermal hydraulic feedbacks may have characteristic time constant in the order of seconds, whereas xenon feedback will be having characteristic time constant in the order of many hours. So it is essential to consider dynamic models of this thermal hydraulic feedbacks along with xenon feedbacks to account for total overall neutronic dynamics within the core. So fission product poisoning within the node can be directly obtained by writing the decay models within the node. So fundamental formulations as shown earlier will be in terms of flux. However, usual change of variables, we can represent this in terms of power. And net reactivity due to xenon or net reactivity due to some other poison like samarium can be directly obtained based on their concentration values. Now coming to thermal hydraulics modeling of PWRs. So PWRs generally consists of fuel pins which are mechanically grouped into fuel assemblies. However, there is no hydraulic isolation among the fuel assemblies. So ideally, when we see a thermal hydraulic problem in PWRs, it is a 3D thermal hydraulics problem, and it is solved in that manner mainly for safety analysis point of view to identify the hotspot or the hottest fuel pin. However, when it comes to modeling approaches for control studies, such elaborate and complex models cannot be directly used. So we resort to two major type of approximations. One is assuming that multiple channels in parallel connected only at the inlet plenum and outlet plenum, so that there is no interaction among fuel assemblies within the core region. Or what we can, one more approximation is a single channel connected only at inlet and outlet plenum, and across the axial direction we assume whatever power that is being produced is being given to the coolant in a form of lumped fashion. So since we generally nodalize the PWRs along axial direction, the second choice is normally followed in modeling the thermal hydraulics core, that heat removal system thermal hydraulics in a PWR. And since most of the PWRs have forced circulation, mass and energy balance are normally sufficient from control studies point of view. the flow will be based on number of pumps that are operating under various operating conditions. However, when it comes to BWRs, these fuel pins are enclosed by flow boundaries, which can be cans, ducts, or channels in case of HWR. So essentially, these fuel assemblies are isolated, and it becomes a 1D problem at assembly level. However, within the assembly, the flow behavior still can be a 3D problem, which is again of specific interest for safety analysis. Again, now since one of the BWR example I have taken is HWR, since nodalization along radial direction is most preferred for that kind of reactors, we follow the approach of multiple channels in parallel connected only at inlet and outlet plenum. However, this BWRs, especially HWR, is having natural circulation. So in addition to mass and energy, we have to consider momentum balance equation also to obtain the governing equations of these thermal hydraulic models, which can be used for control studies. Now I'll try to summarize on how the thermal hydraulic models set of equations looks for a typical PWR and HWR. So this figure shows a simplified schematic of PWR, wherein the coolant from the cold leg enters into the core region, and then it picks up the nuclear heat generated, and it is again transported via hot leg back to steam generator. In steam generator, cold liquid or feed water we call it enters, and this heat from the primary heat transport system or reactor coolant system is transported to secondary system, and the steam generated in the steam generator is transported to secondary cycle. From the modeling perspective, we can consider or divide this entire reactor coolant system into 4 regions. So in the core region, the modeling approach can be as indicated earlier, that we can consider a single channel coupled only at inlet plena and outlet plena. And at the core exit, there is a finite volume of hot leg, which we can denote it as a control volume 1. And heat transfer in SG, we can consider it as a control volume 2, and cold leg, which we can consider as a control volume 3. So what we can really do is we can go for a lumped parameter modeling to account for the transport lags that occur in this hot leg, cold leg, and the heat transfer volume. And in the core region, we can model the system as per number of axial nodes. So within the core region, by writing the energy balance equation and assuming only the convective heat transfer from fuel element to the coolant, these are the set of equations which can be obtained, which define the heat transfer from reactor to coolant. Here we can see that pH, which is obtained from the core neutronics, is coupled to this fuel heat transfer model, and then through convective heat transfer coefficient, this coolant temperature dynamics can be defined. And then these nodes along the axial directions are thermal hydraulically coupled in such a way that outlet from one bottom axial node becomes an inlet temperature to the top axial node, which is residing below that particular node. And then reactivity feedbacks associated with this fuel temperature and coolant temperature can be expressed as a polynomial functions, normally first order or second order polynomial functions. And as indicated, the transport delay in the cold leg and hot leg can be accounted by using simple energy balance in these sections, so that we can obtain a set of first order differential equations in each section. Now when it comes to a BWR modeling, I'll just give a typical example of how advanced heavy water reactor thermal hydraulics modeling is carried out. Advanced heavy water reactor is a vertical pressure tube type boiling water reactor, and this light water coolant picks up the nuclear heat, and then in this two-phase mixture is again transported back to steam drums through a long tailpipe section. And in the steam drums, steam water gets separated by gravity, and the steam is sent to secondary cycle. Same amount of feed flow enters the steam drum in a baffle region so as to avoid mixing of this two-phase mixture, and then this whatever saturated water that is left in the drum that gets mixed with feed water and it is again returned back to the core. This is basically the main heat transport system of a AHWR, and it consists of 452 number of feeder channels, 452 number of coolant channels, and same number of tailpipes. So from modeling perspective, we can consider core region, and we can model this tailpipe region as a hot leg region and this downcomer and feeder region as a cold leg region to account for the transport leg. As indicated earlier, this is a natural circulation reactor, so we need to consider momentum balance equation to obtain the circulation flow, which cannot be considered as a independent parameter. So modeling approaches that are generally used for control studies, one is a homogeneous equilibrium model, in which we assume that both the water and steam phases have same velocity and they are under thermal equilibrium. With this, void fraction can be expressed in terms of the steam quality or the flow quality. This figure shows typical variation of void fraction with various pressures, and then void fraction basically denotes or determines the density of coolant. So depending on the void fraction, we can compute the density, and then depending on the density, we can compute the corresponding reactivity feedback that can be fed back to the neutronics model. The approaches used here are lumped parameter integral average approaches to solve mass and energy balance in each lumped sections. So a typical how we write in core region I'm showing. So we can consider a inlet flow, circulation flow, and an inlet enthalpy to my core region, where some amount of heat is used to convert this single phase liquid into saturated liquid, and afterwards the heat transfer is in two-phase regime. So as it is a compressible flow, outlet flow will not be equal to inlet flow. So we have to write both mass and energy balance equation, and by simplifying this mass and energy balance equation, we can get rid of this exit flow and cast the equations in terms of inlet circulation flow itself. And state variable, one of the state variable will be the flow quality or steam quality. Then void fraction can be directly obtained using a static relation between steam quality and steam quality, and then density can be computed from the void fraction, and from which we can obtain the void reactivity feedback. So equations for other sections also can be obtained in a similar fashion. So in a crux, how the overall model which is used for control studies will look like is shown here. So we have the central part is the core neutronics model, where in each node we have set of differential equations defining the precursor and the power dynamics within that particular node. And then this is coupled with the fuel heat transport and coolant thermal hydraulics model. And then the feedbacks from this model are used internally in the neutronics model. Similarly for xenon and samarium dynamics. And then this thermal hydraulics model is coupled to secondary side, where there is a load demand can be considered as a external input. Through this transport lag, it is coupled with the fuel heat transport and coolant thermal hydraulics model. In addition to this, we have a control signal which we are supposed to control in through design of an automatic power controller. This can be considered as one more input, and depending on the control rod dynamics, we can compute the position of control rod, which itself can be expressed in terms of reactivity due to this control rod. So in this way, we can model the coupled nuclear reactor core and heat removal systems. So such exercises we have carried out for HWR, and also we have done for typical PWRs. And I'll show some of the transient results, open loop transient results, which we have obtained through these simulation procedures. Before going that, one important issue is to obtain the steady state conditions. Since these are highly coupled set of nonlinear equations, a most appropriate approach to obtain the steady state conditions is to solve them iteratively by assuming some initial solution. So right hand side curve shows how one can assume a flat flux distribution and then solve the diffusion equation in terms of an eigenvalue eigenvector problem and obtain the fundamental eigenvector which corresponds to the steady state flux distribution. And from that we can obtain the core power distribution, which can then be fed to the thermal hydraulics model. And then based on the thermal hydraulics parameter, the two group parameters can be recomputed, and we can proceed this in this manner iteratively until we converge on the steady state solution. So there is a significant simulation involved in obtaining the steady state solution also for this set of coupled equations. So a typical response of PWR for load disturbance I am showing here. So figure A shows that there is an initial step reduction in the secondary side power, which we can consider as a turbine power. So the moment there is a reduction in power, so more heat is being generated from primary than it is being removed. So the pressure in the secondary side of the steam generator starts building up, which manifests as increase in the steam temperature. So when steam temperature increases, this leads to increase in the coolant inlet temperature. So when a relatively hot water enters into the core, it will manifest as a negative reactivity to the core, and then the reactor power also starts gradually decreasing. In this way, we can consider that after step reduction, reactor tried to follow the turbine and it tried to stabilize in a global power sense at a reduced power. So this actually demonstrates the inherent global stability characteristics of a PWR due to strong negative reactivity feedbacks. A similar trend can be observed when I again raised back the turbine power back to 100%. So this shows a typical control rod transient where I am trying to add a asymmetric perturbation to the core by inserting the control rod up to 50% from the top of the core, and it can be seen that initial flux distribution got tilted more towards the bottom as the rod is inserted more. Even though the global power again reaches back to the initial value, there is a flux tilt where lower portion of the core will start producing more power and upper portion of the core will start producing less power. When I again bring back the control rod back to its initial position, the flux profile tends to match with its initial condition. However, whatever I am showing here is in the span of seconds, but if left uncontrolled, this kind of perturbations can lead to xenon-induced spatial oscillations, which I have shown in a slide where I am showing a typical xenon-induced oscillations in PWR. This is how we generally model the nuclear reactor and associated heat removal systems in a coupled fashion, and then this nonlinear model is normally linearized at various operating conditions to study the stability properties, and also same will be used in the controller design. I have completed my presentation. Thank you.
Thank you very much to Dr. Shimjith and Professor Tiwari for holding this presentation. It was indeed very, very interesting. Very highly nonlinear problem for control engineers, indeed very exciting. There are already two questions. One question is from Steve Walters, and he says, the topic of interest is the robotic service maintenance of reactors. It is helpful to know thermal fluxes and neutron leakage fluxes under startup, shutdown and outage conditions. Can you model these terms?
Thank you for the question. Yes, such things can be modeled, but the approaches will be different for modeling those conditions. Normally, we try to model using diffusion theory approximation for operating power conditions for control studies. However, same diffusion theory approximation we can start and proceed to model even such conditions.
Okay. Yeah. Thank you. There's another question from Afrin Islam, and she asked effectively about the controller design. Actually, I mean, can I ask if the final, actually simplified model is a linear model or a non-linear model? What kind of controllers are used to manipulate the control rods?
Okay. The first part of the question, I think, is already clear. These are a set of nonlinear model equations. And second part of the question is what kind of controllers are used? Okay. Both conventional output feedback controllers as well as model-based modern control techniques have been applied from theoretical point of view. However, practically till today, static output feedback controllers are only used in controlling the reactor dynamics.
So I would like to add a bit that even though simulations are carried out using nonlinear model equations, the controller design itself is carried out using the linear dynamic equations. Thank you.
If finally you are using linear controllers, then are there any problems associated? Because the actual system is a nonlinear model.
Yeah, we do agree to your observation. It's true, but then it works, really works. The linear control designed using linear control theory that works very well to a nonlinear mathematical model. And as I told in the beginning, our design experience for pressurized heavy water reactors of 540 megawatt, entire design was based on linear control theory approximations. However, the application is to the real plant and it works in a wonderful manner. Thank you.
So are there any operating points you are considering, like for the linear approximation? Okay.
Yes, yes. So generally the gain is obtained at several operating points, and one of the gains varies with power. It is pre-programmed in the algorithm, but design is based on linear approximation. Yeah, thank you. You seem to be taking a lot of interest, so thank you very much.
Yeah, it was a wonderful talk, yeah, and a good learning experience. Thank you.
Yeah, thank you very much. Yannick actually makes an interesting comment. I've never seen a reactor model that integrates xenon and SM poisoning as elegantly as the model you have just presented. So thank you very much. Yeah.
Yeah, we thank you indeed. We thank Mr. Yannick. Thank you very much for that observation.
Okay. Yannick, is there any further comment you want to make or question from your side? If not, but it's interesting. I mean, that you're using a linear controller because it's. I would have thought actually you have to deal quite separately also with the xenon oscillations. Some that you may have to split some actually of your control problems into various parts, and you have to deal with some of the problems quite separately. But it's interesting that the linear actually controller in that sense is indeed very actually sufficient. Yeah. Okay.
Yeah, indeed, it's like that. But as I told, it's a very complex control structure. Even though the design is based on linear principles, there are multiple loops interacting simultaneously, and also the control gains, they vary in a pre-programmed manner as the reactor operates at different power levels. So at different power levels, there can be different control gains.
Okay, so you need to gain schedule actually the whole thing.
Yes, yes. They are pre-programmed. We don't need online gain scheduling. They are pre-programmed depending on the power.
Okay, interesting. Also, as a question, actually, I mean about BARC. Actually, in what sense is BARC actually also involved in ITER itself, and various of the activities on nuclear fusion?
Is SPARC involved in the ITER project?
Yeah, thank you. So there are some people, a small group of people in Bhabha Atomic Research Center actually involved in the ITER project. But we have a little away from Mumbai, a place called Ahmedabad, and there we have Institute of Plasma Research. There, people in large numbers are involved with ITER project. At BARC, we have very few people, maybe a set of 10, 15 people only.
Okay, yeah, interesting. Yeah. And also from my point of view, I mean, I'm curious. I mean, I've seen that BARC, obviously, and you mentioned it, BARC is also interested in robotics. I recall actually there's a lot of teleoperation ongoing as well, isn't it? Interest in teleoperation.
Yeah, you are right. One of our divisions, its name itself is Division of Remote Handling and Robotics. So, of course, we have more expertise in remote handling of some kind of radioactive areas, etc. But some small groups are also working on robotic assisted neurosurgery and some similar medical applications. Like we have a very famous device called as Bhavatron, which is used for what is that called? Radiotherapy.
External beam radiotherapy.
Yeah. So our robotics division is working in these two major areas. One, handling of radioactive, you know, wastes or some kind of equipment, and the other is medical applications of robots.
Yeah, I mean, this overstretching kind of interest is clearly also there with the with Race and Rain, actually Race the group actually within UKIERI, but also Rain in particular actually, which is this project obviously here, which he obviously is organizing this webinar. So yeah, there is actually quite a lot of commonality in that sense. I think we're going now towards the end of this actually webinar. I see there are no further comments or actually questions. I would like to thank actually Professor Tiwari and Dr. Shimjith and for this indeed very interesting presentation. And then from my point of view, close this meeting. Okay, good.